You're fine. You're fine. All right, so sorry about all that. Let me get started here. And see, I wish I had a little bit more time between now and the last meeting, because I'm afraid we're gonna reach a point in this lecture where I'm at a loss, because like the fundamental problem with this section for me is this book, as far as I can remember, doesn't contain a definition of the Riemann integral. And so I'm like, you're trying to show that the Lebesgue integral is the same as the Riemann integral, but you haven't quite defined the Riemann integral. So how exactly did, I think he's assuming, of course, that the Riemann integral has been defined in a proper real analysis course, right? Did you define the Riemann integral in your real analysis course? That's right. You did not get to the integration. Yes, and I think.
I looked at some stuff of my own, but it's been awesome.
Right. So so this is Lebesgue versus Riemann. How do they coincide? And give me a second here. I know, it looks like the board. So to the naked eye, it looks like this board is clean. But in fact, what this board has is it's got the water. They cleaned it with water, and it's just full of streaks that you cannot see, but I can see them, and it's bothering me. It's like, come on, maintenance people, do not use water to clean these boards. It does not work. It just makes them a total mess the next day. You got to use the board cleaner. Otherwise, the board cleaner's got a little bit of wax in it. So it not only cleans, it waxes it, so it makes it, work better. Okay, so here we go. Theorem 2.10. Point 1. It says a Riemann integrable function is Lebesgue integrable, and the integrals are equal. So I'll just abbreviate it like this. Riemann implies Lebesgue. Wait a minute.
If it's Lebesgue integral, sorry, if it's Riemann integral, it's Lebesgue integral, yeah.
And they're equal. All right, so I think as we study his proof, we'll come to some understanding of how he's defined Riemann integral. That's my hope. All right, so he says, let f be Riemann integrable function vanishing outside AB. F be, I can't spell Riemann today, that's not a good sign. Riemann integrable function which is 0 outside, and he says the closed interval, half open interval, the Klopen interval, A to B. And let the value of f be less than m for some constant m. So apparently, without loss of generality, the Riemann integral concerns bounded functions. Right? Otherwise, this would be kind of poor. And that makes sense. I mean, I know this much. So to me, it feels like it depends on how nuanced a treatment of Riemann that you've given. Like, I think a lot of people, when they teach calculus, they just treat Riemann integrals for continuous functions. But certainly you can extend the concept of Riemann integrals to finitely many piecewise discontinuities. So then if it's piecewise continuous, you define the Riemann integral to be the sum of the integrals of the continuous pieces. And then since you can prove theorems on the continuous pieces, then you can just string them together and there's finitely many things, so the gluing together works. I mean, I think that's my idea of it anyway. Okay, so he says for every n, we partition the interval AB into n intervals of equal length. All right, so for each n in n, partition AB into intervals length. I'm going to give it a name, delta x, which is going to be b minus a over n. Although he calls this c, and I guess I like the notation c since I'm about to write this a kabillion times, but here it is, a comma. You know what? I don't like c. I like delta x because that's what it is. There we go. Haha. Oh, wait a minute. Like this. And then you've got a plus delta x, comma a plus 2 delta x. Right? And this goes on. Again, he uses c instead of delta x, and maybe I'll be driven to it before too long. But I'm stubborn, so I'm going to still write the delta x here for a second at least. N minus 1 delta x to a plus n delta x. Of course, what is a plus n delta x? I mean, yeah, this is literally b though, right? Okay, great. So he's just taking the interval, he's chopping it up into n subintervals of equal length. And then he's going to say we define gn of x equal to, here we go, the infimum of f of t such that t is an element of the closed interval from a plus, huh? Okay, let me, this is one of those, this is kind of like that example the other day. A plus, wait a minute, what? Nah. Fine, let me finish writing it. I don't believe it. I don't believe this makes sense, but I'll finish writing it and then we can decide, okay? Okay, so that's the Clopin interval that closes the infimum, and then he says if x is an element of that same Clopin interval, all right, and it's 0 otherwise. So, like, I think that's supposed to be n.
I think it's supposed to be to some particular k in the natural since we're doing arbitrary.
See, if it's, yeah, I mean, like the other one, there was a condition on the k that made it a little bit, this is not like that. I think this is just a typo. It makes more sense to me if n is, if it's just supposed to be n instead of k over there. Or alternatively, you could erase that n and make it a k. So what do you want? You don't care? Here we go. Waha. I believe. And then he lets h sub k of x be equal to the supremum of f of t, such that t is an element of, all right, this is Pac-Man sub k. If x is an element of Pac-Man sub k. All right, and 0 otherwise. And then he says, since G sub n is a bounded, non-decreasing sequence of functions, it's a bounded, non-decreasing G sub k. G sub k is a bounded, non-decreasing sequence of functions. Does that make sense? Why is it decreasing?
Is it non-decreasing?
Why non-decreasing?
Well, it's bounded, obviously, because of it exists coming from the partition of the
Oh yeah, the bounded is the, I get that.
I guess it's because when we keep adding these k minus 1 times delta, k is greater than or equal to 1, and delta x is always positive. So, oh, we're talking about the function itself.
Bounded non-decreasing sequence. Why is it non-decreasing? So in other words, so let's see, non-decreasing in what sense? Like, I mean, I would assume that means that should mean not non-decreasing, right? In this context, it should mean what? Yeah, it should be non-decreasing means for me, it means my usual increasing. This is horrible.
Right, yeah.
Which to me then means that, since we're talking about a sequence, it should mean that gk plus 1 of x is what? How does it relate to gk of x?
And it should be greater than or equal to is okay.
Right, great, yeah, exactly. Greater than or equal to. The equals to is what is the usual.
Yeah.
Why is it that if we put k plus 1 versus k, like, is that clear? I thought that these were, I thought these were like, I'm confused because it seems to me like Pac-Man, I mean, I could be wrong, but my feeling about this is that Pac-Man k plus 1 intersect Pac-Man k, man, I'm glad I gave it a label. I think that's empty. I mean, am I wrong?
No, I think you're talking about the function itself, though. So it's like every zero.
That's not quite true. Oh, that's literally true. This is literally true. However, they do bump up against one another. Like for example, let's look at Pac-Man 0. Excuse me, Pac-Man 1 goes from A to A plus delta x, right? And then the next one goes to A plus delta x to A plus 2 delta x, right? So that's Pac-Man 2, let's say. And it is true that they're disjoint. But notice we're not using min, we're using infimum, which means that.
Well, it's in infimum the function values evaluated though.
Right. So like, basically, if as you take a sequence approaching this a plus delta x point, right? if you take a sequence as approaching a plus delta x point, and that's where the minimum happens, well, the infimum happens for that,
Yeah.
then effectively f of the point, I mean, what I'm trying to say is the inf of Pac-Man 1 could in principle be a plus delta x, f of a plus delta x. That's like, that could happen. And so,
That could happen.
so if that, well, more to the point, f of t has to be less than or equal to f of a plus delta x for all t in Pac-Man 1 in this guy, right? Because, well, not f of, but the I shouldn't say f of t, but the inf.
Yeah.
The infimum of that has to be less than that.
Oh, yeah, duh, but that's, okay.
Because,
Oh, I think
and so that means that this is smaller than that,
yeah.
but then this, right?
Oh,
And then this is smaller than the infimum
Infimum
of f of s, let's say, for all s in, Pac-Man 2.
Yeah.
And so that means then that it's getting bigger.
Yeah.
That means it's increasing. So he really does mean it's increasing. Now they could be equal, so it's not non-decreasing because the equality is possible. Sorry. So that's actually subtle.
Yeah.
Yeah, that's actually kind of subtle. I'm kind of surprised I figured it out, honestly. You got to understand, I woke up at 2:30 or 2:40 today, and I started writing calculus notes until about 8, and then I'm not sure what happened, but anyway, I'm a little bit tired. So, oh no, it's my own fault. I fell asleep at like 8 last night or something, so it all evens out. But all right, so we have a non-decreasing sequence of bounded functions, and I now believe it, and it converges at every x in R. Well, he says since Gn is a bounded non-decreasing sequence of functions, it converges at every x in R. And he says define g of x equal to the limit.
Is that about the monotone convergence theorem just for sequences? Since it's bounded and increasing.
Let's see here.
And given whatever x, the sequence of functions boundary that x.
Which theorem did you say it was?
That was the monotone convergence theorem from
The monotone.
analysis 1. The monotone convergence theorem is first
Well, it's not quite Fatau's lemma. If a sequence of integrable function converges almost, no, that's not it.
It's not.
The sequence of,
Not in Hilbert Spaces book.
oh.
Just,
I don't know. I'm sorry.
No, you're fine. Sorry. No,
You're fine. You're fine.
I think it makes sense, but I was.
Let's see here. So we have this.
A monotone sequence of real numbers is convergent if and only if it's
A monotone sequence of real numbers is convergent if and only if it's bounded.
And so since
Oh, yes, very good. You're right. We are using. Oh, thank you. I should know this. I covered this in Calc 2 this week of all things. The bounded monotonic sequence theorem, of course. Yes. So we for each x, it's a bounded monotonic sequence, and So yeah, so it has to, the limit has to,
It exists.
has to exist. And we call that limit, we let that define g of x in that way. And then he says the functions gn, I've changed the k to n now, sorry. The functions gn are integrable, being step functions, okay. Oh, they are step functions, aren't they? Because they're just constant on each subinterval, aren't they? They're equal to the constant, which is the infimum on each subinterval. They slipped that past me. They are step functions, though. And thus, by the Lebesgue dominated convergence theorem, G is integrable. So, hence, by Lebesgue dominated convergence theorem, G is Gn or G words. G is integrable, and keep in mind that means Lebesgue integrable, and the integral of G is equal to the limit as n goes to infinity of the integral of Gn. And likewise, h of x equals to the limit as n goes to infinity of hn of x as it's also Lebesgue integrable, and the integral of h is also equal to the limit of the integrals of the step functions that are composing h. Right? No, you're fine. I already moved it.
I'm sorry.
It's okay. It's okay. It's really fine. And okay, so do you understand it would, instead of non-decreasing, it would be non-increasing, right? It's like, it's a very similar argument to the one we gave, but with supremum instead of infimum, it goes the other way. Yeah, it's non-increasing. And the Lebesgue dominated convergence theorem also holds for non-increasing sequences of bounded. Well, I mean, we could read it again. Probably wouldn't hurt. I will find it eventually. Here it is. If a sequence of integrable functions converges almost everywhere to a function f, and there exists an integrable function h such that the absolute value of fn is less than or equal to h for every n, then f is integrable and fn goes to f in norm.
Yeah, okay.
So,
This is converted everywhere.
yeah, so it's
Everywhere.
exactly, it's by construction almost converging, so it converges almost everywhere. So that's the almost everywhere, and the fact that it's less than or equal to h, I think, is also. Yeah, that's by the, right.
Gotcha.
Yeah. Okay, so then here's the thing that, depending on your treatment of Riemann integrals, might be a little bit of a surprise. Because I think it would definitely be a surprise if you read the treatment of Riemann integration, which is in, I don't know, like Stewart. I mean, not to pick just on Stewart, but I don't feel like the thing he's referencing here isn't like in a lot of the standard calculus books anymore. But here it is on the other. But then again, maybe he's really referencing real analysis, right? That's an assumption that people reading this book have had a course in real analysis that got to the proper end of real analysis, which of course is not actually the case at many schools because of various societal pressures. But he's like, the integral, the limit, so the limit as n goes to infinity of the gn's is equal to the limit as n goes to infinity of the hn's. right? The idea here is,
Because the integral is unique.
so I think, well, yeah, you could say uniqueness of the integral, but the idea here is like a lower or an upper approximating sum to the integral, and like one of the characterizations is like the lower approximations and the upper approximations have to converge and be equal for the function to be Riemann integrable.
Is this the like Darboux?
Is it Darboux? I think Darboux is a, I don't know right offhand what is I'm not an expert in integration by any means.
I haven't
Not that that's something only our experts know, but
read this section yet, but I think I remember.
yeah, these are the upper and lower integrals, is what I'm saying.
Okay.
I mean, if you really look at LF and UF, that's essentially, we're not exactly calculating that. See, okay, so here's the difference: is this Darboux integral you're reading about? It's done over arbitrary petitions, right? You notice already we started with a petition of equal length.
Yeah.
Okay, so if you read Howard Anton's calculus, which is not a real analysis book, but in Howard Anton's calculus, he doesn't set up the integral in terms of a limit of n going to infinity. He sets up an integral in terms of delta x going to 0, where the delta x going to 0 is taken over like all possible partitions, and he doesn't insist delta x be the same width across all the different integrations. It's really sophisticated, honestly, compared to what you find in like Stewart, which is equal width partitions, and I don't think really there's much even discussion of upper and lower sums, if there is any in Stewart. I have to look again, but part of my impression of Stewart is colored by the fact that I used Stewart calculus and concepts in my first teaching with it, which is a garbage version of it. Anyway, so this would be like, upper and lower sums being equal. That's something that is given to us by the Riemann integrability. If we're all right, so then what? Thus, the integral of h minus g absolute value is equal to the integral of h minus g is equal to the limit as n goes to infinity of integral hn minus gn, which is equal to 0. He says, hence, g equals h almost everywhere, and as g is less than or equal to f is less than or equal to h, we have, well, g equals to f equals to h almost everywhere. And he says this proves that f is Lebesgue integrable. And they're both equal, both being equal to the limit as n goes to infinity of g sub n. So. Oof. Huh. All right, so yeah, that feels right. I mean, again, to be fully satisfied, I would need to have in front of me the complete and technical definition of the Riemann integral, And we don't have that, so we just have to count on that whatever treatment of Riemann integrals you have, if you make it careful enough, part of it has to be that the upper and lower sums of the integral have to match up. I mean, yeah, we sometimes, I think the way it's stated in Stewart is like all possible approximations for the area have to converge to the same thing for a Riemann integrable function, something like that. So the way I teach it to students is always like, it doesn't matter if you use the left or the right or the midpoint rule, they all converge to the same thing, and that thing is the area, right? Well, that's true as long as the function that you're integrating is Riemann integrable. So if you have a function which is not Riemann integrable, well, that might not happen. So anyway, continuous functions are Riemann integrable. All right, let's go on to the next claim here. All right, so theorem 2.10.2. So he's like f be Lebesgue integrable. Function unbounded or unbounded AB and let A less than or equal to C less than or equal to B, then big F of x equal to the integral from C to xf is continuous in AB, and limits f of a is like going to be equal to the limit. So in other words, it's continuous in the interior of the set, and it's also naturally continuous in the endpoints like this. Although if I read this correctly, he's allowing the case that a and b be infinity or minus infinity. You know? And these limits exist in our finite. So let me see here. Let me take a step back and say what we're saying here. So we're saying that if you have a function which is Lebesgue integrable, and then you define a new function, right, by integrating that function from a given point, a given reference point C, then the resulting area function is necessarily continuous. So while Lebesgue integrable functions certainly include discontinuous, in fact, horribly discontinuous things, the process of integrating smooths that out. It's one way to think about this theorem. So how do we prove this? Well, let's see. So he says, let x be a point. Oh, you got it right. Cool. Let x be a... This is in the way. Let's see here. I don't know why I don't move that. I work around it. I'm an idiot, you know? So proof. So x with a less than or equal to x less than b, all right? And he wants x sub n, a decreasing sequence in AB convergent to what? Well, to x, all right? So what does that mean? It means that x is less than xn plus 1, but that is less than xn, and that is less than b. So we have those estimates, right? And xn goes to x. Okay, great. We got it. All right. He says, let g sub n be defined by the characteristic function of the open interval from x to xn for n equals to 1, 2, 3, and so forth. All right. So what's going on here? Those are step functions, right? Yeah, I mean, close to. Setting aside the issue of x not, I mean, fine. I mean, I have the Klopen. All right. And so he's like, then the sequence of products FGN converges to 0 at every point of AB. So if we put that of x, he says that goes to 0 for each. I shouldn't use x here. I probably should use like t, because x has a different meaning, yeah? For each t in AB. Well, let me think about that for a second here. What I'm debating is whether or not x is fixed here. Well, anyway, it's still, I mean, no, that's fine, it's fine. So what happens as n goes to infinity? As n goes to infinity, right? This, right, as this n goes to infinity, this shrinks to just the point x, right? So,
characteristic function is supposed to be going to 0 then as we approach the single point x.
Yeah. Oh, that becomes the as it approaches x, that becomes the empty set. So x is not in there. It's just literally 0 everywhere. Yeah. This is fine. This is fine. Yeah. This is okay. I got it. All right. So then what? He says since absolute value of f gn is less than or equal to f, all right? Why is that true? Oh, well, duh. I mean, because this g is either 1 or 0, so that's just the value of f times gn is literally either 0 or the value of f. So this is true. Fine. We have, where's the big F? Oh, he's, all right. Let me say here, let big F, right, because we haven't said that yet, in the proof at least, the big F of x equal to the integral from c to x of little f, all right? And, all right, so then we can look at big F of xn minus big F of, I guess technically I should use a different, this x should be, let me use a t here just because I still feel like that x was fixed in the other argument. I'm still not, I'm still a little, I'm still debating whether or not that x is still fixed or not. So let me just, anyway, so fxn minus fx equal to the integral from, he says it's the integral from x to xn of f. See, okay, fine. Okay, fine, mister. Did I miss it? Did we ever prove these kind of things for these kind of integrals? Because I don't remember it. Maybe we did. Maybe I'm just forgetting it. But I don't remember that we ever proved that. I mean, I think it's true. Maybe that's, you know what, this is probably in the homework I haven't done. That the integral, it's the thing I was mentioning at the start of everything as being something that was really technical to prove for the Riemann integral, but. So like this, so first of all, if you, so C, where is C in all this? C is ostensibly between, where's the C? Oh, okay, so that's the thing is, no, this is it. Well, curses. Well, if we put C equals to X, if we put C equals to X, right? Then this is equal to the integral from X to Xn of F. Sorry, I'm just. Don't mind me. Let's see here. All right, well, let's suppose we don't do that. Then this would be the integral from C to Xn of F plus the integral from C to X, right? I mean, X to C, rather. If you flip the bounds, and then supposing that C is between C, but can I assume C is between Xn and X? Like, this feels all wonky to me. But if I could, then this would then be integral from X to Xn, you know?
Well, if C is equal to that, well, no.
If I don't put this, if I just assume C is between. All right, so there's. Just a second. Let me just draw a number line and just sort through things here for a second. So Xn is here. X is over here. Right? If C is in the middle, then this is, I think, reasonable, and this simplifies back to X to Xn, right?
Right. If it's right, if X and then it's tangent to X.
Right. What if C is over here?
Yeah.
If C is over there, then the integral from C to Xn has to be understood as minus the integral from Xn to C, because these are in the wrong order. And when you take the integral from X to C of F minus the integral from Xn to C of F, that is equal to the integral of so you're going, this one would go from X all the way over to C, and then you're subtracting the one that goes from Xn to C, right? So what you're left with is Xn to, or X to Xn rather. So it doesn't matter whether C is between the points or to the right or to the left. It's actually always, well, it can't be to the left, but I don't think it can be to the left. I guess it could be. A is less than or equal to X. I don't know. I think you could probably even come up with if C was over here, it probably still works out. So maybe he's just not, I believe. Okay, it doesn't matter where C is. So then what? Can I erase?
Yeah, you're taking pictures.
Oh yeah, yeah. Go for it. Let me get my. We good?
Yes, sir. Yeah.
All right. So then this is equal to the integral from a to b of f gn, and that goes to 0 as n goes to infinity. But the reason it goes to 0 is by the Lebesgue-dominated convergence theorem. So, so he says, thus, f is right-hand continuous at x in AB and has limit a. Thus, f is right-hand continuous, so goodness gracious. So he's saying the limit as, let's say t goes to x from the right of f of t is equal to f of x for each x in AB. And so he right-hand continuous, and he says likewise, you can prove that the limit as t approaches x from the left of f of t is equal to f of x for x an element of AB as well. So if it's left and right-hand continuous, then it's so if the left and right limits exist and are equal, then of course it follows that it's then you have the double-sided limit exists, and of course that suffices to prove continuity. Excuse me. Golly. And then he says, okay, so by he says since f is right-hand and left-hand continuous, you get the endpoints for free. Like these, of course, these then you've already proved these as well. Okay, yeah, great. So, but interesting. So it's a straightforward consequence essentially of the convergence theorems that we had, the Lebesgue-dominated convergence theorem. Everything's Lebesgue-dominated convergence theorem, isn't it? All right, so let me see here. Where are we? There are we. All right, so I think I'm gonna move on here to the definition of measurable set. If you don't mind, I'm gonna skip the last part of that section. I don't know. I mean, we could go through it if you want, but it's up. Yeah. So, I mean, what I'm skipping over is the fundamental theorem of calculus being true for the Lebesgue integral, and the change of variables theorem being true for the Lebesgue integration. If we have time at the end of this week, I'll go back to them, okay? I've only got about about 5 or so, maybe 10 minutes left here before I got to go. So, so we're now in 2.11. I just want to at least get started on this, which is measurable set. And so here it is, a set S is called measurable if the characteristic function is a locally integrable function. He says, to every measurable set, we assign a non-negative number or infinity, which is called the measure of the set. So here's the definition. Let S be measurable set. If the characteristic of S is an integrable function, then the measure of S is denoted mu of S, and it's defined to be the integral of the characteristic function of S. And then if the characteristic function is not integrable, then we define the measure of S to be infinity. He says null sets are sets whose measure is 0. And he says the following theorem gives a useful tool for proving that a set is a null set. All right. So let's see here. Theorem S, a subset of R, is null set if and only if for each epsilon greater than 0 there exist intervals A1, B1, A2, B2, these are Clopin intervals, dot, 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 such that S is a subset of the union n equals 1 to infinity of an, bn, such that and not just that, the sum n equals 1 to infinity of the difference b sub n minus a sub n is less than epsilon. Proof of that thing is a page. So it's a null set if and only if for each epsilon greater than 0 you can find this, this sequence of intervals of vanishing length, essentially, right? So this is this condition that the sum of their differences is less than epsilon is sort of saying, as n goes to infinity, the size of those is getting small, as you like, and right, because and this has to be able to, you have to be able to do this for each epsilon greater than 0, right? And then the next theorem here, after the page proof of that, is if you have S1 S2 disjoint disjoint measurable sets. All right, then S formed by the infinite union of these guys is measurable, and mu of S is equal to the series formed by adding the measures. So, no, you're fine. I'll just scooch over here a bit. So, all right, let's just, now, this doesn't have to be, this is understood, it could be I think this could be a divergent series, right? So disjoint measurable sets. Yeah? There's infinitely many of them. So let's just, for the remaining time today, just try to look at some like concrete things about this idea. What would the measure be, for example, of just the open set, A to B? What would the measure of that be? The integral of the characteristic function AB, right? Which is? B minus A, right? So demystifying this a bit, the idea of measure is essentially to capture the length of the set. It's just the length of the set, basically. And so to say it has measure 0 in some sense is say the set has length 0 in some kind of sense. And so, if you want me to, so for example, disjoint measurable sets. Of course, you could you could take this, right? N plus 1, right? Union n equals 1 to n equals let me be minus n. I'm trying to get the whole real line. I think I can do it. Well, let's do it this way. N to n plus 1 like that, right? N equals 1 to infinity. This gives me 0 to infinity, right? In terms of the set theory. Oh, thank you. Yeah, 1 to infinity. Yeah, thank you. Thank you. Very good. 1 to infinity. What's the measure of these guys? Well, it's 1, right? So, of course, this theorem that I wrote last is sensible in the sense that the measure of each is 1. It takes infinitely many of them to form the whole 1 to infinity. So it follows then that the measure of 1 to infinity is equal to the sum n equals 1 to infinity of 1, also known as infinity, right? That ray, the ray to infinity, has measure infinity. So I think it's one of the interesting things about measure is it's one of these examples in mathematics where we meaningfully use infinity as part of an extended number system. If you study analysis in terms of I want to say like the supremum and the infimum, like there's a way of using infinity and minus infinity to fully extend those concepts that you'll see in the better analysis books. But so listen, we'll start more or less here next time. My goal next time is to finish up what I have to say about measurable sets and to at least sketch the ideas in the remaining sections, which I think we'll have enough time in an hour to do. So thanks, guys.